Good afternoon, everyone. I would like to welcome you all for my webinar about case study of integral bridge structure. Basically, I would like to share my experience of designing one of the longest integral bridges in the UK. Before going to the webinar, I have got an announcement on behalf of MIDAS that this webinar will be a CPT webinar. So those who wish to receive a CPT certificate, there will be a short survey at the end of this session, so you can request through that survey. And please note, the CPT certificate is only available for UK attendees. So we are going to talk about integral bridges and overview, and case study. Today's case study topic is Fort Valley Viaduct Bridge. In that, we are going to discuss about construction stage analysis, creep and shrinkage, thermal action and its application, earth pressure application, and results discussion. So to begin with, I would like to give a brief introduction about our company. I work for a company called AECOM. It's an American multinational engineering firm, a global design leader, providing design consulting, construction and management services to a wide range of clients. And about myself, I hope you have gone through the invitation. If not, you can always search for my name in LinkedIn to get my professional introduction. Because I don't want to spend too much time on introducing myself, because there are a lot of stuff to cover in the following slides. Some quick facts about AECOM Credentials. We have generated a revenue of approximately $20.2 billion US during last financial year, and for the 5th consecutive year, we are named one of Fortune magazine's world's most admired companies, and we are ranked #1 in transportation and general building in engineering news records 2018 in top 500 design firms. Our core values are safeguard, collaborate, inspire, anticipate, deliver, and dream. And we hope that that's why our clients value us. And our commitment is always safety first, and sustainability in all our projects, and corporate responsibility as well. AECOM has got diversified expertise, and as you can see in this slide, we are into airports, we are into tall buildings, cross rail, bridges, hyperloop, and many more to count on. And in particular, to discuss about bridge projects, these are some of the iconic projects that AECOM has delivered in the past. You can see it's a high-speed rail, suspension bridges, cable stay bridges, iconic pedestrian bridge in Northern Ireland, lifting bridge, and so on. In this section, we are going to see an overview of integral bridges. We are going to talk about what is an integral bridge, why an integral bridge construction is required, different types of integral bridge construction, and earth pressure distribution, along with live load surcharge models. What is an integral bridge? An integral bridge is a structure where the expansion joints are not provided to accommodate enlargement due to thermal variations. The expansion and contraction, the movement due to expansion and contraction is accommodated by the abutments itself. As you can see from this snippet below, the abutment and the deck are monolithically connected. I have idealized this in the picture here. So you can see the difference between a simply separated bridge and an integral bridge. In a simply separated bridge, the movement due to thermal expansion or contraction is accommodated by expansion joints, whereas in integral bridge, it is accommodated by the abutments itself. Why integral bridge construction is required? Durability. It is a key factor in designing of bridges these days, as this has lowered down maintenance problems and liability issues to councils and highways England or any other client. Continuous structures have proved to be more durable than simply supported decks, mainly because simply supported decks through the expansion joints have allowed salty water to leak through and get the structure corroded. So that's the reason the simply supported decks are not preferable in terms of durability, and continuous structures are always preferred, and especially the monolithic structures like integral bridges are preferred. BD5701 recommends the bridge structures to be designed as continuous or intermediate supports. It also recommends that the bridges with lengths not exceeding 60 meters and skews not exceeding 30 degrees shall be designed as integral bridges. It doesn't say that if it exceeds 60 meters that it cannot be an integral bridge or something like that. It can be, and also if there is a deemed necessary to prove, to have a simply supported bridge, then it needs to be approved by overseeing organization. So this slide talks about de-icing salts and its effects. As you can see here, the corrosion that is caused from de-icing salt on this picture. And this is a bridge collapse in Canada due to corrosion from de-icing salts. Let's discuss about different types of integral bridge construction. Frame abutment, that is a solid wall abutment, bank pad abutments, embedded wall abutments, semi-integral type abutments, flexible support abutments. In this webinar, we are going to discuss about two types of integral bridge construction. That is, one is a frame abutment, solid wall abutment, and the other one is flexible support abutments. In the flexible support abutments, the earth pressure is not applied to the columns as it is sleeved, and the earth pressure is only applied to the end screen, and that is the diaphragm portion. We will discuss this later. Earth pressure distribution and live load surcharge models. So this subtopic I'm going to discuss about strain ratcheting, earth pressure distribution for a conventional abutment wall, for an integral abutment wall, the two options. So there is full height and flexible support abutments, earth pressure distribution for wing walls, and live load surcharge model for abutment walls, and a brief comparison between BS5400 and PD6694, and live load surcharge model for wing walls. I am referring to PD6694 here because Eurocode 7 doesn't explicitly mention about earth pressure distribution and live load surcharge model. Let's talk about soil structural interaction at abutments. Due to thermal expansion and contraction, integral bridges are subjected to many thermal cycles, that is, repeated backward and forward movement of the abutment. This repeated backward and forward movement of abutment generates extra pressure on the backfill that tends to a maximum value with a pressure coefficient of K star. So that is, if you can see my mouse pointer here, so when thermal expansion and contraction occurs, so this abutment tends to move backward and forward here, and because of that, this disturbs the soil, the backfill, and this creates, after many thermal cycles, this creates an additional pressure that will be much higher than active earth pressure. So this enhanced pressure with a pressure coefficient is called as K star, and it is dependent on total movement of the end of the deck from its maximum contraction position to its maximum expansion position. That is from 0 point to the center of the bridge. Say, for example, if the bridge length is 140 meters, then the maximum expansion position to maximum contraction position is from 0 meter to 70 meters, half of the length of the bridge. There is another way of applying these earth pressures to the abutment. That is finding out the equivalent spring stiffness. A number of studies have looked into the ways to calculate these spring stiffness. But out of that, the one which is published by Barry Lehane has gained a significant popularity because of its satisfactory performance. It also includes, considers the nonlinear behavior of soils, and it accounts for ratcheting effects as well. In MIDAS Civil, it is possible to model this equivalent spring stiffness through its tools. In Fort-Wiley Viaduct Bridge, we have used enhanced earth pressure application, the earth pressure loads, rather than soil springs because of its simplicity. This slide shows earth pressure distribution for a conventional abutment wall. Sorry. As you can see, for a conventional abutment wall, it is a triangular earth pressure with the Ka and a rectangular distribution for live load surcharge. Whereas for an integral abutment frame abutment wall, it's going to be triangular for half height of the abutment wall, and it's going to be trapezoidal from half height to the bottom of the wall. Remember, this earth pressure is not Ka, it's going to be K star because of the reasons that we have discussed before. That is a strain ratcheting. PD6694 clause 9.4.3 gives the equations to calculate this K star for this type of abutment wall, and is going to be different for a flexible support abutment wall, that is with the reinforced earth structure along with the monolithic diaphragm and columns. So for this type of end screen wall, the earth pressure distribution will be triangular as shown here, and the equation to calculate this enhanced earth pressure is given in clause 9.4.4 of PD6694. Next, we'll discuss about earth pressure distribution for integral bridge wing walls. It's a triangular distribution for the wing walls, but only thing is that the K star that we have calculated for the abutment walls, that has to be multiplied with the active earth pressure. So the net pressure has to be applied to the wing walls, bridge wing walls, as a triangular distribution. We'll talk about the live load surcharge model for abutments. Table 7 of PD6694 gives in detail of how to apply the live load surcharge and the equations to calculate the live load surcharge value. This figure shows the application of live load surcharge model. That is, it contains two line loads that has to be applied within a lane width at the top of the abutment as a horizontal load in global X direction, and apart from that, there will be another load that is a UDL load that's going to be applied to the entire height of the abutment wall. So it's basically two components, line load and UDL. Coming back to this slide, this table gives you the live load surcharge equation for LM1 and LM3. So basically this one is for LM1 and this is for LM3. You can refer to the equations here, and these are with factors R, LF, that is lane factor, and dispersion factor. So you may need to use these factors to find out the magnitude of the live load surcharge. This slide shows the comparison of surcharge between PD6694 and BS5400. I'm sure most of them are familiar with BS5400. So I would like to bring this slide to just to compare the surcharge, live load surcharge. In BS5400, the HA loading is 10 km per meter square, but it's only UDL. There is no line load component on it. For LM1, it is line load. The line load is 109 kN. If I consider assuming that KD as 0.33, R as 1, and LF as 1, and UDL is 6.66, whereas for HA it is 10 kilopascal, and for LM3 the line load is same, assuming the factors shown below, and the UDL is 9.9 kilopascal. And the UDL is for HP 45 units is 20 kilopascal. So this is a difference between the live load surcharge between two different codes. So this is a surcharge model for wing walls. As you can see, the distance between the CG of the wheel to the edge of the that's the face of the wing wall plays an important role in the distribution of the in the dispersion of this surcharge pressure. So as you can see here, the pressure distribution is going to be inverted triangular distribution, and figure 3 of PD6694 gives a equation to calculate the magnitude of this force. So let's go into other sections, 3, that is Fort-Valley Viaduct Bridge, our case study topic. So in this section, we are going to discuss about project brief, project location, different viaduct options that were considered in the design before finalizing the current detailed option, and structural details and some 3D visuals. To give some brief background of the project, so we are the detailed design consultants, and we work for client Balfour, contractors Balfour BT. Fort Valley Link Road is a proposed 1 kilometer road linking William Prance Road in Derriford to Fort Valley Road junction. The project is in Plymouth. This project is to basically ease the traffic congestion in the nearby areas. As you can see here, this is a 1 kilometer link road that is connecting from this point to here to the Fort Valley junction. In this link road, our bridge is somewhere here at the end, and the length of the bridge is 140 meters. So let's see what options that we have considered that were in our table for design. There is a choice of structure type and backfill materials, and choice of abutment for integral construction. Let's see what are those. So the structure type, we are not quite sure whether to go with integral or semi-integral, because the length of the structure exceeds 60 meters. So it can be a semi-integral, but the problem is if you go with semi-integral, then there will be a maintenance liability to the client. So then we later decided to go with integral structure, even though it is a bit complex, but we want the structure to be durable. Whether to go with 4-span or 5-span, we're not quite sure, and then we have analyzed for both span condition, and then finalized with 4-span. Backfill material, we got 3 options. 6 and 6P backfill, it's a traditional backfill, you all know. Lightweight backfill and geofoam EPS blocks. Lightweight backfill is a bit expensive than 6 and 6P backfill, and the EPS blocks is expensive than these 2 material. So we started with the 6 and 6P backfill and a lightweight backfill, and then we have finalized with 6 and 6P backfill itself. As we went for flexible support abutments, we use 6I6J in combination with 6 and 6P. And then the choice of foundation type, to go with either pile or pad. Pile foundation, it's a flexible system. It will accommodate thermal movements, huge horizontal loads, but it is time consuming, expensive. But pad foundation, it is a rigid system. It's structurally stiff. It generates huge pressure on substructure. It needs a wider base to accommodate the large horizontal forces. This slide shows EPS backfill to the abutments. I just want to show you all that how a EPS block looks like. Nothing to do with the Fort Valley project. We haven't used this, but I just want to show you all how a EPS block backfill looks like. Choice of abutment wall. So this is the main thing. We had 2 options. Whether to go with the full height abutment wall or to go with the sleeved column for abutments. One is a stiff structurally stiff system, another one is a flexible system. So we started with the full height frame abutment wall, and for that analysis, we ended up with the 4 rows of 9 numbers of 1200 dia pile for both abutments. Pier 3, it was anticipated to be piled, and Pier 1 and 2 ended up with band foundation. Whereas sleeved column abutments, here we eliminated the earth pressure on the abutment columns, as the columns were sleeved with manual rings, and because of this we are able to reduce huge earth pressures on the abutment walls, and because of that, and also we used longer piles. The system become more flexible, and we ended up with 3 rows of 9 numbers of 900 dia pile for both abutments, and all piers were found to be on pad foundation. So this is isometric view of 2 detailed options. So the first option is the full height abutment frame model. It's a stiff structural system. We tried with for pad foundation first, and then it went for, but it didn't work out. So we went for pile foundation then. And the option 2 is a flexible support structural system with end screen abutment walls. As you can see here, the columns, the earth pressure was completely eliminated on the abutment wall, on the column, on the pier columns, as it was sleeved, and it was applied only to the diaphragm wall. This slide shows an example of stiff and flexible structural system. So mainly the portal frame is dependent on the modulus of rigidity, moment of inertia, and the length of the column. So it's A by L cube. So we have used this system for the main model, but for this webinar purpose, I have just created a simple portal frame model to show how the length factor plays a major role on reducing the forces to on the structural system. I have assumed a 35-meter long span portal frame with the 5-meter height column, and use the same properties for the flexible system. That is the next one. Just change the height of the column to 11 meters. So this is the reaction output. As you can see, when the column height is shorter, that is 5 meters, the temperature, the reaction from the temperature load, I've applied at 35 degrees Celsius uniform temperature to this model. So the reaction from this thermal action is about 5,160 kilonewton. Whereas for the same load case, for the same loads, for the same span, with same EI, just changing the height of the column, you can see the force has dropped down drastically to 760 kilonewton. So that's what I want to convey you all, that instead of using a pad foundation, please prefer for a pile foundation if it is possible, if your ground conditions permit, for long span structure, for long bridges like for valley. So if you're planning for an integral bridge structure, long integral bridge structure, at least for abutments, please go with piled foundation system if your if the soil conditions permit. So this is the bending moment output of the same case. You can see it's 23,700 kilonewton meter for the SIF system, and it is 7,085 for the flexible system. The whole point is to make the system, the structural system, flexible, just to make, reduce the effects from thermal actions. So based on this studies, we have finalized the option 2, that is a flexible structural system support abutments with sleeved columns and reinforced earth wall system. So this is the plan view of the bridge. As you can see, the bridge is 140 meters long here, 35 meter each span, 4 spans here. This is the reinforced earth wall system, reinforced earth wall wing walls here on all the 4 corners. The bridge deck is 25 meter wide with 3 lanes, 3 traffic lanes, 2 westbound lane and 1 eastbound lane, and 2 shade for footway on either ends. This is the bridge elevation. As you can see here, the bridge abutments are piled on the pier or pad foundation. This pier 3 was I mean we were able to change this to pad foundation because we have used sleeved columns for the abutments. This is the bridge deck cross section. We have used 7 number of W16 beams with 220 mil deck slab on top of it. This is the elevation view, the abutments. You can see the columns are inside the sleeves. The one which you're seeing here is the manual rings, and the columns are inside these manual rings. So the earth pressure is going to be applied on the manual rings, and it's not to the structure. So this is the longitudinal section. As you can see, the diaphragm deck and the abutment columns are all monolithically connected. The earth pressure is only applied to the end screen wall, that is the diaphragm portion, and beneath that, the 6x6J backfill, it's all reinforced earth system. It is not this doesn't create any earth pressure to the abutment columns. So this is a plan view of the pier section. So there is a gap between the manual rings and the column section, and this is to be filled with a filler board. This is the pier section. You can see the pad foundations and some 3D visuals of the bridge. Okay, so let's discuss about shrinkage and creep. For any integral bridges, the second order effects plays a critical role in the analysis. So we have to consider the creep coefficient and shrinkage strain at different days of construction, and it has to be defined in the construction stage analysis. So in this section, we are going to discuss about a brief introduction about creep and shrinkage, compressive strength, and time-dependent material link that we are going to see how to do it in MIDAS model. So as you all know, creep and shrinkage are time-dependent properties. It is dependent on the ambient humidity, the dimensions of the element, and the composition of the concrete. Creep is also influenced by the maturity of the concrete and the duration of the loading, the time of the loading, and the magnitude of the loading as well. These effects are to be primarily considered for SLS case, but if it needs to be considered for ULS case, then the criticality of the structure has to be seen. If it is like a structure, if a structure like integral bridge, then the creep and shrinkage effects has to be taken for ULS case as well. Creep coefficient and shrinkage strain. Eurocode 1992, clause 3.4 explains about this creep coefficient and shrinkage strain. Annex B gives basic equations to calculate this creep coefficient. And clause 3.1.4 point number 6 gives talks about the shrinkage strain. Basically, the shrinkage strain is composed of two components. One is autogeneous and the other one is drying shrinkage strain. Autogeneous shrinkage strain, it develops during the hardening of concrete itself, that is from day one itself. And drying shrinkage strain, it is a factor of, it's a time dependent thing. So it develops slowly as a function of migration of water through the hardened concrete. Equation 3.11 of 1992 code gives the calculation for autogeneous shrinkage strain, and Annex B of the same code gives the basic equations to calculate the drying shrinkage strain. Sorry. So let's see how these coefficients and strain are calculated in the MIDAS Civil. So so you can go into the properties and click Creep and Shrinkage tab. So this window pops up, and you can click Add button, so that this window pops up, so where you can define the parameters. You can give some name like PS. If you're defining the parameters for beam, just say PSC beam, and you can choose the code, European or whatever standard you want to choose you're designing to, and you can define the compressive strength of concrete for 28 days at the age of 28 days, and you can choose the relative humidity. I'm assuming 70%, but it varies. And notional size of member, again it depends on the cross section of the member, but I'm assuming as let's say 0.59 meters. The type of cement. So people usually tend to see which one to select, whether it is class SN or. So I'll give a brief for which one to choose. So usually class R can be assumed unless if the cement contains 35 to 65% of GGBS, use class N. If the GGBS content exceeds 65%, use class S. So for time being, we can assume that there is no GGBS content, so we can assume class R. And type of code, concrete bridge code, and age of concrete at the beginning of shrinkage, let's say day one. And if you click this tab, show results, MIDAS automatically calculates the creep coefficient and shrinkage strain. So if you want to view the results, you can click the creep coefficient here, and you can view the results here at each and at particular days, and it can be visualized in a graphical format. And if you want to change the loading, let's say if the loading starts at 5th day, it changes automatically here. And if you want to check the shrinkage strain, click on this tab, and you can see the shrinkage strain. This can be verified using the codal equations that we have discussed before. I have done it, and I have done a comparison, and it is okay. So both values are matching. Going back to our slide. So next thing is compressed strength. Sometimes when you're using when we are defining concrete parameters in construction stage, we may need to define at particular days. It's not always we are using 28-day strength. We may use 14-day for PEC elements, or 15-day, it depends. So code gives basic equations to calculate the compressive strength at T days. You can refer to clause 3.1.2, which gives this equation. MIDAS Civil does this again automatically. So what you will need to do is just give the input parameters, So when you go to properties, click on compressive strength here. So this opens up a window, and you can choose a name. You can assign any name and type. If it's to be like a code, if you want to calculate based on the codal equations, just click this code and then choose the code, which code you have to use it, and give the mean compressive strength, that is the 28 day strength plus 8 megapascal, and choose the class type, cement type, that is class R, that we have choose, and for the creep and shrinkage properties. So once these parameters are defined, if you just click this redraw graph, then the compressive strength at various days, at each day, is shown on this graph. So the software software has calculated from 0 day to 30 day and so on. The next thing is time dependent material link. So once these two parameters are defined, the creep and shrinkage and the compressive strength, so we need to let the software know that these two parameters are to be linked for a prestress beam, or for transfer slab, or whatever material that you would like to assign these properties. So for that case, so we need to tell the software by using this material link property. So please go to properties, material link. When you click that tab, a tree menu opens like this, and where you can choose the creep and shrinkage that was already defined, and the compressive strength for that parameter. So choose those two, and from your list of materials, select the material that has these properties, and use this button to take this other side of the table, and from there just click add, so that now this material, so now by doing this, we are telling the software that this material has got these properties. So that's the basic thing for time dependent material link. Sorry. Now we'll discuss about construction stage analysis. But I'll take you through the model itself. So this is the complete model of the Fort Valley Bridge. This is the base model. For any model to be developed, it has to be developed in a base model, that is here, base. And then once the parameters are defined, once the loading condition, boundary condition, elements, properties, everything, then it has to taken to the then it has to be taken to the construction stage analysis or the definition. So to define the construction stage, so main thing is all the elements, boundary condition, and the loads has to be grouped like this. I'm just showing like that. So pier, I have grouped all the elements like piers, abutments, piles, abutment columns, diaphragms, beams. All these elements were grouped here as a structure group. And then the boundary condition, like beam and releases, rigid links, elastic links, point spring supports, all these were grouped here. And the loads on the structure also needs to be grouped as shown here. So let's go into the construction stage. I used 10 different construction stages here. So the stage 1 is the construction of foundation and substructure. Stage 2, erection of span 1. Stage 3, span 2. Stage 4, span 3. Stage 5, span 4. And then stage 6 and 7 is the deck pour concrete in simply supported condition. Stage 7 is over the piers and abutments. So until this stage, the bridge is going to behave as simply supported, and once after this stage, it becomes composite. So you can see how it varies here. And then once it becomes composite, you can apply the loads after it becomes composite, such as surfacing, parapets, if any, and then the wedge loads, and then the long-term loads. So let's go into the let's go briefly into the construction stage. So this is how a construction stage definition looks like. So you need to click on you can generate this construction stage by selecting the elements, boundary condition. So what you need to do is basically you just need to select all these elements and then push it to activation stage, choose the age, and then choose the boundary conditions and choose the loads that are to be defined to that construction stage. Likewise, you can create various stages. And another thing what I wanted to discuss is about the deactivation. So as I said before, until stage 7, the structure is going to behave as simply supported. So the wet concrete loads and the boundary conditions, these has to be slightly modified. Like the one which was defined in the simply supported case may not no longer needed for the composite stage. So for those situations, so you may need to deactivate some of the boundary condition or the loads. For example, wet concrete load that are used in the stage 6 here has to be deactivated in stage 8 because the composite section property comes into the picture in stage 8. If the wet concrete load is still there, then it doubles up the self-weight of the deck slab. That I don't want to do that. So that's why it has been deactivated. So likewise, boundary condition, the beam in releases that were used in construction stage for simply supported condition can be deactivated to make the structure as fully integral. So this is a brief about construction stage, and we'll move on to next topic. Thermal action and its application in MIDAS Civil. So in this subsection, we are going to discuss about uniform temperature component and vertical temperature component with non-linear effect. Also, I'd like to mention a point that thermal contraction will lead to minimum earth pressures, but it is we don't need to worry about the gap forming, because when thermal contraction occurs to the structure, there might be a gap creating between the backfill and the structure, but it is not a thing to worry, because the daily thermal movements will make sure that this will not occur. Thermal expansion of the deck, it leads to maximum earth pressure. That's going to govern the case for abutment wall. Thermal actions, it's mainly uniform temperature, linearly varying temperature difference component in both directions, and a non-linear varying temperature difference component. These effects were from daily and seasonal changes in shade air temperature, solar radiation, etc. And this will affect the elements of the structure. So first we'll discuss about uniform temperature component. I believe most of them are familiar with these things, but still I just want to highlight a few points that the air shade temperatures, that is a Tmin and Tmax, shall be derived from the site project specific location, and this has to be adjusted for sea level. And once that has been adjusted, then according to the type of the deck, the Tmin and Tmax shall be calculated. Once that is calculated, again it has to be adjusted for the deck surfacing, as shown here in National Annex. Once the Tmin and Tmax has been adjusted to deck surfacing, the final temperature, uniform temperature component has to be applied into the model. So these, so before applying, these many adjustments shall be done. That's what I would like to make a point here. So let's see how to apply this in MIDAS Civil. It's fairly simple. Choose the beams that that you want to apply the uniform temperature component, and then go to the load tab here. Choose the temperature, and then go to element temperature. Click this element temperature tab. Once you click that element temperature tab, you can choose the load group name, load case name, and then make sure this initial temperature is 0 for degrees Celsius. If it is Fahrenheit, then it has to be changed accordingly. And the final temperature that we have calculated after all the adjustments is 33 degrees Celsius. Just input that and apply. So once that is applied, so you can see the temperature, uniform temperature component is applied to the beams. So next thing is the vertical temperature component. We are going to have a live demonstration on how to apply this vertical temperature and nonlinear effect. Our bridge is a concrete bridge, so the blocks, the heating and cooling blocks given in figure 6.2c is applicable. I'm sure you all are familiar with this table. MIDAS Civil, actually it considers the blocks as a rectangular blocks. So there is a key thing that needs to be considered. So before going into the live demonstration, I would like to tell that our cross section, bridge cross section, has to be changed into, has to be idealized as a equivalent rectangular cross section. That is, now this W beam, it has got two webs, so it has to be idealized as a one rectangular section. So for instance, what I'm doing here is I'm taking the average web thickness here to average web thickness of these two webs and assigning as a one component, one rectangular block with this depth and this width. So for the deck slab, it's straightforward. It is a rectangular one, so we don't need to disturb that. And for the soffit of the W beam, so this has to be again idealized into a proper rectangular block. That is, the idealized section is here. That is 1.5 meters by 0.22 meters. Now let's see how a heating block, stress block is created now using this idealization. So from this heating, I'm going to discuss only about heating because of the time constraints. So you can see this from the code. This gives the formula for H1, H2, and H3. So I have calculated H1, H2, H3 based on this W beam section for the valley bridge. H1 is 0.15 meter, H2 is 0.25, and H3 is 0.22, and 0.3 times of H is 0.666. H1 as a calculator here is 150 mil from top, that is from 0 to 0.15 here. So H1 is going to be here like that. So the first block here, I'm going to define the first block here. That is the width of the H1 is going to be 3.6 meters. That is here, that is a B. And H1 is 0. That is starting from 0 point and ending with 0.15 H2. And temperature that is defined in the code for this heating for this type of structure cross section is 13 degrees Celsius. That is, the total height is more than 800 mil. So it starts with 13 degrees Celsius and it drops down to 3 degrees Celsius. So on the second block, it is the H2, that is from 0.15 meter to 0.4 meters, because our H2 is 250 mil. So it starts from 0.15 meter and it ends at 0.4 meters, height of 250 mil. But here the thing is, it cannot be one block as we did for the deck flange, because the section is varying here. So this has to be broken into 2 blocks. The first block will be representing the deck slab, that is from 0.15 meter to 0.22 meter. And the next block component is from 0.22 meter to 0.4 meters. That is the width of web. But thing is, we need to manually calculate using similar triangles what will be the temperature component at 0.22. So I have done that already. So that is 2.16. So the second block will be the width of the second block will be 3.6 meters here, and then the H1 will be 0.15, varying from 0.15 to 0.22, and T1 is 3 degrees Celsius. That is from the code. That's here, T2, and it goes up to 2.16 at the bottom of the deck slab. That is calculated using similar triangles. So, and then the third block, since the width is changing, so we need to define the width accordingly. So here the width is 0.61, that is defined here, and then H1 is 0.22, that is from the bottom of deck slab to 0.4, that is the end of the H2. And the temperature is varying from 2.16 to 0. The fourth block is straightforward because it's 0.22, and fortunately our thickness of bottom flange is also 0.22, so there is no need for 2 different blocks. So I'm going to apply this straight straight. So the breadth is 1.5 meters and H1 is 2 meters. Sorry, 2, and then H2 is 2.22, and the T1 is, it is starting from the temperature starting from 0, and it is ending to 2.5. So this is the main thing. Once it is in hand, then it is very simple and straightforward to apply in MIDAS Civil. Let's see how to do that. So you can go to this, go to load, temperature, and then choose a beam section temperature. You can choose, as I said, all the groups, all the loads has to be grouped. So you can see temperature rise, that's the group I have defined for heating. And then again, you can choose a load group name. General and PSE, the difference between these two is general is for the sections which I have shown now. We need to calculate, the user has to calculate manually if this section type is selected. If PSE section type is selected, the software calculates automatically based on the section that is defined in the property section. So it's mostly applicable for box girders, standard box girders, or composite section. But for our webinar, we'll go with general, as we have calculated the stress temperature blocks. Direction, local Z, that's Z and Y, so we are referring to the vertical one, Z. And reference position is N top, because we are here in our Excel sheet, we are referring from top. It's everything is from top, not from the centroid. So choose this N top, and just input the parameter here, B as 3.6. And H1 is 0, H2 is 0.15, T1 is 13 degrees Celsius, and T2 is 3 degrees Celsius. And click add. Because of time constraints, I'm not going to add other temperature blocks, but it's the same thing. So you've already calculated that, and just input here and click add. So all the 4 blocks will be here. Once it is there, and then select the beams that you want to apply the temperature force. I'm just selecting randomly, and say if you click apply, so this will be applied like this, but you can do it properly. So that's the application of non-linear temperature action into the in MIDAS Civil. And then going back to our slide, so earth pressure distribution and its application. So I would like to briefly discuss about the design to abutment walls. That there are three cases. That is, case one is maximum thermal expansion plus maximum bridge loads. Here, the creep is a relieving effect, and so you can omit it. And case two is maximum thermal contraction plus minimum bridge loads. You can include the creep and differential temperature. And case three is maximum thermal expansion plus minimum bridge loads. The creep and differential temperature can be included. So out of these three cases, one case is going to go on the abutment wall design. In most cases, it will be case one. And just giving some quick facts that if you are considering case star earth pressure, traffic surcharge loads can be omitted. It doesn't need to be considered together. And then, but the traffic surcharge loads needs to be applied to one abutment if active earth pressure is considered. So let's take a frame abutment wall. I have calculated the earth pressure with K star coefficient that is varying from 0 to 387, 387 to 111. First is the triangular distribution, and the rest is the trapezoidal distribution. Let's see how it can be applied in MIDAS Civil. I'm just choosing the notes. So I'm going to apply this earth pressure distribution to the model now. So it starts from 0 to 387. The total height of the abutment wall is 10.5 meters, and the half height is 5.25. So this is a half height node here. You can go to load. Please select hydrostatic pressure, and don't confuse with the name. So this is a load type to define the earth pressure. Choose the load case name, choose the load group name. So plate, and the global direction is global X. And here, reference level, select the first top level, that is 10.5. And then constant intensity is 0, so it is varying from 0 to 387. Since this 387, since this gradient intensity is in kilonewton per meter cube, this has to be divided by the length of the application, that is 5.25. So the total height of the wall is 10.5, half of the height is 5.25. So I'm going to divide this 387 by 5.25. So that is 73.71. So I'm going to apply that here. So now this triangular distribution has been applied, and then again to apply the trapezoidal one, click this, and then this should be 387. And then the gradient intensity, as I discussed, it needs to be difference of the two loads, that is 387 minus 111, again divided by 5.25, gives the gradient intensity. Since it's a trapezoidal, the direction is changing, it should be applied as negative. Sorry, I haven't selected the element. Yeah. So when you go to the loads and then display, so you can see the loads has been defined exactly as what we are seeing here. So 0, 387, 111, 0, 387, 111. So that's the application of the earth pressure loads, case earth pressure load. Going back to the slide. So we'll discuss quickly about the results as we're running out of the time. One thing I would like to tell to you is that to you all is that when you're taking the results, please make sure that the loads that were defined in construction stage, the results has to be taken, the relevant results has to be taken from the construction stage itself. So for example, if you have applied a sulfite in construction stage, so the results has to be taken from construction stage and not from sulfite, sorry, not from post-construction stage. So if you're referring to construction stage results, so dead load, I'm sure most of them are familiar with these results, but I just would like to show how it is for Fort Valley. So you can see this is a dead load sulfite of the beams bending moment diagram. And if you choose the sulfite in post-construction stage, then it is not right, because you can see in post-construction stage sulfite, the loads are much higher. You can see the negative moment, the supports, but it is not the case, because it assumes that the bridge structure is integral from day one, but that's not the case. It will defeat the whole purpose of construction stage analysis. So the results that you're going to take has to be carefully chosen from where it has to be taken, whether it is post-construction stage or the construction stage. So in post-construction stage, you can take the results like moving loads, earth pressure loads, temperature loads, and so on. There is another way of extracting these results, that is from results table, beam. You can go to the force, and then you can choose the elements, and then click the elements, I mean the load case that you want to take the output, and click. If you click OK, so it will be in a table format. You can copy this into Excel sheet and sort out the results accordingly. So going back to the slide, so now we are into the final slide, conclusion. So in this slide, I would like to tell you about the utilization of MIDAS Civil in this case study. We have put a lot of technical expertise in designing this Fort Valley viaduct bridge. We have carefully forethought about the process, everything, and to support us, this software MIDAS Civil has greatly helped us to choose between this type of abutment, whether to go with flexible or frame abutments. Since this is a compressed structure, it was very difficult. It is to model all the elements. As you can see, there are a lot of elements to model: beams, columns, foundations, etc. And different section properties. For construction stage, it needs to be only beam only property, and again it has to change to composite property. Likewise, different section properties, and a lot of parameters to define as well. And indeed, the load inputs, you got about 50, more than 50 load cases, earth pressures, thermal actions to include, and various construction stages, and number of boundary conditions like beam and release, rigid links, elastic links, spring supports, deactivation, activation, where to activate and where to deactivate, and different moving load combinations as well, and the results to design each and every element, the results to be extracted is like it took a lot of time. It would have taken a lot of time if MIDAS Civil is not in place, and the load combination as well. We got about more than 60 load combinations for this bridge structure. So what I would like to conclude is like we have applied a lot of technical expertise for this bridge project, and we have successfully and efficiently designed this bridge using MIDAS Civil. So that's it, and thank you for your time, and I hope that you all enjoyed this webinar and found it very useful. Thank you.